So ultimately the goal is to be able to sketch out this function. If we take all the stuff that we've been doing here lately, like finding first derivatives, setting up tables, finding second derivatives, and setting up tables, let's keep following that pattern, because that's supposed to be useful information for us to be able to sketch a function like we got here on number 4. So if you start with this first derivative that's been given, and you dissect it like we've been doing, what we do with the first derivative, we look where the first derivative equals 0. We look where it does not exist. Where the first derivative equals 0, you take your numerator, set that equal to 0, and solve. Where it does not exist, you take your denominator, set that equal to 0, and solve. So where f prime equals 0, if I solve for x, x is going to be 0. Where f prime does not exist, to get rid of the squared quantity, you take the square root of each side. Right, that takes care of that part. If you're solving for x, x squared would equal 9. Take your square root. Don't forget the plus or minus. It'd be plus or minus 3.
Why do you get rid of that? X one?
Why do you get rid of which part?
The X one.
Right here? I'm taking the square root of each side. Now, if we were asked to find critical numbers, if that was the question, this is where we'd say C equals, for our critical numbers, -3, 0, and 3. However, for it to be a critical number, it has to be a number that's in the domain of the function. So notice, if you take -3 and 3 and plug back into the original function, it doesn't work. So technically, the only critical number here is 0. But as useful numbers go in setting up our chart for all this increasing, decreasing stuff, right, as useful numbers go, we want to take these values and use those to set up the chart. So even though -3 and 3 are not critical numbers, we're still going to place them over here. We set up the first derivative chart.
You said they're not critical numbers?
-3 and 3 would not be critical numbers because they're not in the domain of the original function. Right? If you took those numbers and plugged back in, they didn't work.
Where does it say domain? Could you hypothetically just, never mind, you're recording now, keep going.
That's fine. All right, as we set things up here, we're going from -infinity up to -3. Got -3, -3 to 0, pause at 0, 0 to 3 is the next interval, pause at 3, and then 3 to infinity as our last interval. As we've gotten in the habit of doing already, at these key values of -3, 0, and 3, we note in the first derivative column basically how we got those. So at -3 and 3, we know that the first derivative does not exist. Right, that was the category we got those results from. And at 0, we know the first derivative equals 0. Okay, now we play the plug-in game where we take numbers on these intervals, we plug into the first derivative. So that's this guy up here. We see what kind of sign results we get. So when I take a number that is on the interval from -infinity to -3, something less than -3 like -4, if I plug that into my first derivative, do I get a positive value back or do I get a negative value back? If I plug in -4, it's -2 times -4 on top, right? That's positive. Divided by a quantity squared, which will always be positive. Positive divided by positive, it's going to be positive. I choose a number on the interval -3 to 0, also a negative number. So I choose -1. I'm going to get the same thing back, right? Same thing I got for that first interval, so that's going to be positive. From 0 to 3, on the interval 0 to 3, say I choose 2. I plug in 2 to the first derivative. -2 times 2 is negative on top. It's going to be negative divided by that positive quantity. That's going to be negative. And same kind of thing should happen here at the bottom, right? Because I'm just choosing another positive number. When you plug in and do the calculations, you get a negative back there. So what these signs are supposed to tell me about the original function that ultimately I'm going to use to sketch this graph out. All the positives tell me where the function goes up. All the negatives tell me where the function goes down. And as extreme points go, any relative maxes or mins, we're looking for changes in direction. We only see the one change in direction. We go from up to down right here where x is 0. When we go up to down, that's a relative maximum. And if we know that's a key point, we're going to take 0, and now we plug back into the original function because it's a point on that function. If you plug 0 back into the original function, well, let's see, I'm going to have 1 over 0 squared minus 9, so that's going to be negative 1/9. So there's all our first derivative stuff found as usual. So moving on from here, we do the same kind of thing with our second derivative. You take your second derivative, explore where that second derivative equals 0. Explore where it does not exist. As far as where it would equal 0, numerator was 6 times the quantity x squared plus 3. We set that equal to 0. Denominator is x squared minus 9 as a quantity cube. We set that equal to 0 for the does not exist stuff. On the equal 0 side, if I'm solving for x, I could divide both sides by 6 to cancel out the 6. X squared plus 3 would equal 0, so x squared would equal negative 3. If you take the square root of each side, that's not going to work out so well. So on this side, we're not going to have a solution, right? We don't get a result from that side. On the does not exist side, kind of like when we solved this side of it for the first derivative, here we'd take a cube root of both sides. The cube goes away. In solving for x, you should notice that we get the same kind of results back. And that should happen for all this does not exist stuff, because after all, those values are not in the domain of the original function anyway. But if we follow the process the same way we have been, we'll always get those results back. So we take those values, we set up our chart based off of those values. It's a second derivative chart this time. So what we're exploring is concavity. We're looking at the curvature for the original function. That means that inflection points might be something that we can come up with here. As you set up your intervals, we're starting at negative infinity again. We're going up to negative 3. Pause at negative 3. Go from negative 3 up to 3. Pause at 3, and then 3 to infinity. If you acknowledge basically how you got the values negative 3 and 3 for the second derivative, that came from the does not exist part. Now take values on these intervals, plug back into the second derivative, and see what kind of sign results we get. Something that's less than negative 3, we choose negative 4 again. We're plugging back in here to the second derivative. If I plug in negative 4, let's see. I'm going to square it on top, so ultimately that's all going to be positive. I'm going to square it on the bottom. Ultimately all that's going to be positive, even though I'm cubing it. So it looks like this will be positive. If you take a value on the interval from negative 3 to 3, say 0, because that'd be easy, plug into the second derivative. Now let's see, 0 goes in. It's all positive on top. Be a negative 9 cubed on the bottom, so that's going to ultimately be negative. A positive divided by a negative is negative. And then if we take a value from 3 to infinity, say 4, we plug in, should end up with the same thing we did when we plugged in negative 4. So that's positive. What all the positive signs tell us about the function? It tells us that the function is concave up. for those intervals. What all the negatives tell us about the function. It tells us it's concave down. Now, when there is a change in concavity, we have inflection points. So if you look at the change in concavity here from up to down, we have an inflection point at -3. From down to up, we have an inflection point at 3. At least it would seem that way, right? But the problem is, if you take these numbers to plug back into the original function and find those points, it's not going to work. They're not in the domain, right? So we actually have no inflection points.
Why?
If you take -3 and 3 and plug back into the original function, you get errors. Doesn't work. Yeah, -3 and 3 are not in the domain of the original function. So the last thing, now we've gone back and basically reviewed all the stuff that's pretty current. The last thing we need to consider, we're kind of going way back now. You'll notice on these problems we asked you to find x-intercepts. We asked you to find y-intercepts. We also asked you to find asymptotes. So vertical asymptotes, horizontal asymptotes. I don't believe on any of these problems you guys are doing we'll have to worry about the slant or oblique asymptotes, so we'll stop there. But really, this is the last of the information we need, or if we transfer this stuff over, we can come up with our graph if we use all those charts as guidance as well.
What is an oblique asymptote?
An oblique asymptote, like a slant asymptote, is a specific type of oblique asymptote. But basically, an oblique asymptote occurs when the degree in the numerator is higher than the degree in the denominator. All right. It's horizontal asymptotes, if you recall, we're looking at degrees to help us figure those out. If we start with the x-intercepts here, recall x-intercepts occur when y equals 0. So everything we do on this page here, we go back and we use the original function. If I use the original function, I replace y with 0. 0 would equal 1 over x squared minus 9. Now, if I try to solve that, I'd be multiplying both sides by x squared minus 9 to clear the fraction. And once that clears, I'm multiplying a 0 over here. It'd be 0 equals 1, which doesn't work. So all that means is for your x-intercept, since we didn't get a solution, there's just no x-intercept. We're not going to be able to produce a point here that ultimately we can plot on our graph. For the y-intercept, we replaced all the x's with 0. So original function, y equals 1 over 0 squared minus 9. If you solve for y, that gives you your y-intercept. Y is going to equal -1/9. So our y-intercept point is 0 and -1/9, which actually was a specific point produced from one of our charts. Okay, that's a coincidence. And unfortunately, it doesn't really give us a new point. Reviewing how to find a vertical asymptote. This is where you take your denominator. You set that equal to 0, and you solve for x. So denominator here, x squared minus 9. I set that equal to 0. I solve for x. Feels like I've been doing this one a lot. Should make sense for a vertical asymptote that you've been doing this one a lot, because this does reconnect back to your domain. We have two vertical asymptotes. X equals -3 and x equals 3. Finally, the horizontal asymptote. Last key piece of information we need to find. For a horizontal asymptote, you compare the degrees in the numerator and denominator. In the numerator, looking at that degree, you're looking at the highest power of x. There's no x, so degree is 0. looking in the denominator, highest power of x is 2. Whenever the degree is less on top, what is the horizontal asymptote? Remember? Y equals 0. There you go. Whenever it's less on top, y equals 0 is the horizontal asymptote. Whenever the degrees are the same, that's where you divide the coefficients. And then that gives you your asymptote value. Okay, let's see what we can take now from all this work we've been doing and try to piece together a graph. If I stay on this page, a good rule of thumb to follow is start plotting points if you've got them. This whole mess of work, we got one stinking point. So let's plot it. 0 and -1/9. We got a y-intercept. We also know it's a relative max based on one of those charts we came up with. There's 0 and -1/9. Other useful information from this page. We've got the asymptotes we can draw in. Got 2 vertical, 1 horizontal. So at x equals 3, x equals -3. I'll draw in those asymptote lines. And y equals 0 is my x-axis, so I can identify that here. All right, once we've established any key points, we go back, we start using our charts. Ideally, we go back to the first derivative chart and we start filling in directions. So this is where we kind of lightly sketch things out. I go back to that first chart. As I identify the directions here, I've got 2 intervals where the graph is going up, right? I've got 2 intervals where the graph is going down. So if I sketch in the general idea for those directions, it says from -infinity to -3 for my x's, which would be all of this right here, basically this whole section, the graph is going up. If the graph's going to go up, that means you could start down here, but it wouldn't make sense to start down there because you have a horizontal asymptote. And the way these graphs work, that horizontal asymptote's got to guide the end behavior of the graph. So you need your direction going upwards, starting above the asymptote, and basically going this way. Now I'm kind of anticipating what's happening with the curve. But remember, the curve stuff, that's second derivative stuff. We'll get there in a minute. Right now I'm just focusing on direction, so I lightly sketch that in. Next interval is -3 to 0. So this whole area right here, graph is going up. The graph's going to go up. You know it's got to hit these points you've been plotting. So it's going to have to come up basically from down here and hit that point. I'm making some assumptions about the curvature, but I at least got the direction right. I know what happens when I assume, yes. From 0 to 3. So this whole vicinity right here, graph is decreasing according to that chart. So it has to hit this point, it has to decrease. It's basically decreasing to that asymptote, so it makes sense that it goes down, something like that. So I lightly sketch that in. And then when I get to 3 to infinity, which is all this stuff, graph's supposed to go down again. Now if the graph's going to go down, we could start down here and draw down, or we could start up here and draw down. It makes sense to start up here because of what you know about vertical asymptotes and what you know about horizontal asymptotes. Once again, horizontal asymptote, this graph has to be guided by that horizontal asymptote with its end behavior. Now, it looks pretty much like we got an accurate graph going here for the function. But just to make things official and make sure we understand the concept, we go back to the second derivative chart. On the second derivative chart, we've got 2 intervals where the graph is concave up. right? From negative infinity to negative 3, from 3 to infinity. We've got one where it's concave down. So if we transfer that understanding over, and we kind of exaggerate the curves a little bit to fit those qualifications. From negative infinity to negative 3, this whole area, graph is concave up. So we got the increasing part in, the concave up. If we exaggerate this a little bit, we really already had the concave up in there, but that would definitely be concave up. And then from 3 to infinity, which is this vicinity out here, also concave up. We pretty much got the idea in play, but we'll exaggerate it just to make sure. That is definitely concave up. It's concave down from negative 3 to 3. So from here to here in this area of the graph, all curvature must be downward. Once again, we got a pretty good start. I exaggerate a little bit more. I can conclude now that everything you see in blue here is a sketch of the original function.